Good afternoon, all. Today, I'm going to talk about one of the mega projects called 30-meter telescope project and India's participation and what India is doing and so on. This talk is in fact part of ongoing AE lecture series by ARIES Nainital. If you have questions, please feel free to ask and write your comments, and we will answer towards the end of the lecture. So once we say 30-meter telescope project, it means we are talking about a quantity called 30, and this 30 is nothing but the diameter of the telescope. So once we say 30-meter telescope, it means we are talking about a very large telescope having diameter of 30 meter. So why this 30 meter is important is following. So if you see this a very simple schematic diagram where a ray of light is falling on the primary mirror and reflecting back to secondary, and again reflecting back to a sort of plane mirror and fed to different instruments. So that's how schematic of 30-meter telescope is, where the primary mirror is of 30-meter diameter. Why this is important? For these following two reasons, A and B. That is, larger the size of the primary mirror, that is aperture, farther the distance one can see, and that way flux or number of photons are proportional to size of the aperture. It means if you have a 3-meter diameter telescope and if you have a 30-meter diameter telescope, it makes a difference because it goes as d square. So 3 square or 30 square, it makes a difference of around 70 times or something like that. So that's what matters, that the light gathering power increases. Second, larger the size of the primary mirror, better the resolving power is. That is lambda by d. It means if you have a 3-meter class telescope, then d being in denominator makes a difference in resolving power, and once you put is maybe 10 times larger, that is 30, then it's all the way a very different game and your resolving power increases a lot. So that's how we are talking larger and larger optical telescopes, because increasing diameter means increasing d, and that's how it contributes to the whole game and understanding the universe to a different perspective and so on. So once we talk about diameter, you can see in India in 90s we had Venubapu telescope in 80s, and it was having diameter 2.3 meter and it was completely indigenous. And recently we had 3.6 meter diameter Devastal optical telescope, that is in 2016. So all the way from 80s to 2016, we reached from 2.3 to maybe 3.6 meter diameter, though around similar time scale the world was already using 5-meter diameter telescope to a 10-meter diameter telescope, for example Keck. And as you can see that from single monolithic mirror we have evolved to a segmented mirror technology, and that's how diameter is increased from 2 to 3 to 4 meter to maybe 10 meter. So with this perspective, you can see that we were really far behind, and when world is already using Keck 10-meter class kind of telescope, and in future we are already planning to have a 30-meter telescope, it means we are, the world in general, plans to use a larger diameter telescope so that those unanswered questions about the evolution of universe or universe in general could be answered, which is not known yet or which has not been explored so far. that is always trying to understand something which is in the knowledge domain area called unknown unknowns. So that's the importance of larger and larger telescopes and why they are required. How we entered into this game is following. It's important for us to understand that around 2006, 7, 8, three large telescopes in the world projects were going on. That is 24.5 meter giant mirror telescope, and then 30 meter telescope, and then 39 meter European extremely large telescopes. All these three project people, they approached India whether we would like to participate, and that's how this whole exercise started back in 2007. So the evaluation process itself, the evaluation process lasted for over a year. What we discussed is that what is the need for participation, which one would be the most suitable project, and what kind of participation do we really need, and whether it is going to help us to let our astronomical needs fulfilled. So based on this exercise, the community chose that probably 30 meter telescope, that is TMT, at the level of 10% level participation would be the best option for us. It was decided so because it was giving a sort of guarantee in-kind contribution, and based on segmented mirror technology, the Keck heritage was already there, well-established technology, and it was a rather smaller group, but we had a larger say, and it was also giving a good synergy with existing northern hemisphere facilities. So based on all these broad criteria, we decided that finally India would go to 30 meter TMT telescope. So at the level of 10% partnership. So from 2007 to 2014, a lot of exercise were done, development of consensus among scientific community of India, the proposal development, technology demonstration, prototyping phase of various components, and so on. And that's how the fund approval and cabinet approval for this project was done in 2014. And agreement signed by the Union Cabinet Minister of Science and Technology in the same year towards the end of the year. And from 2015 to 2019, execution of partner work packages, what kind of work we can do, what are capabilities, and how can we really contribute was exercised to a large scale. And we established that actually really we can do something constructive towards the project. Meanwhile, one small thing happened that in Hawaii, the site, the on-site construction was rather stalled, and due to some litigation aspects, and now it seems that it has been resolved. So from 2020, we expect that in next 10 years or so, the construction of the TMT International Observatory, that is TIO, will start, and execution of work share and all work packages whatsoever have been allotted to India and other partner countries would be completed, and development of human resources and readiness to use the facility of 30 meter class would be done in this next coming 10 years. And that's how we believe that from 2030 to maybe 2080 would be the period for scientific operations. So this whole exercise will last for 50 long years, and in these 50 years we are expected to learn a lot about the unknown aspect of the universe, which has not been yet understood. All right. So as I said, let me little more emphasize that what do we have in ATs? That is 2.3 meter Venu-Bapu telescope, and from AT to in next 35 years, we came to a 3.6 meter class telescope, where the world was already using between AT's 4 to 6 meter class telescope. from 1990 onwards, the astronomical community in the world was already using 8 to 10 meter class telescope. And then when it was decided that we will have a TMT, that is 30-meter telescope, it was already a big gap for India because we did not have our own 8 to 10 meter class telescope. We had just 3.6 meter Devastal optical telescope after a lot of struggles and so on. That is only recently. So it was a good choice, and we decided that let's have a big jump and join to the best, where actually rest of the world will be using in coming decades and so on. So that was the idea, that is access to the best and bridging the gap. So that was a kind of challenging climb what India had decided, and we are going ahead with this motive that we would have access to the best in coming decade or so. All right. So if you see where the world is in these kind of mega optical infrared facilities, that is giant segmented mirror telescope by 2020s, then as I said, there are three telescopes, 30-meter telescope and giant mirror telescope. It's all US based project, as you can see. And in TMT, not only US, we have Canada, we have China, we have Japan and India. In GMT, as you can see, apart from US, we have Australia and we have Korea. Whereas EELT is actually a European facility, and it is going to be based in Chile. And that's how, as you can see, that very few countries in the world will have this kind of facility in coming decade. So with the India definitely cannot miss this chance to join one of these large projects so that it can be one of the leaders in coming decade among optical infrared astronomy. So what is TMT collaboration and what kind of things do we have? So as you can see on this world map, here is the site called Monarchia, and as you can see, Delhi and Beijing, and then you have Tokyo, and then you have Washington and California for that matter, and then we have Canada. So that's how it's a centrally located place, and it was decided that Monarchia in Hawaii is the kind of best northern hemisphere observing site for optical infrared astronomy, and that was the motive behind having Monarchia as a possible site for this 30-meter telescope. And here is the real picture of Monarchia, where you can see these are the two twin Keck telescopes, and this is 10-meter class facility. Then you have Subaru and other larger facilities, and we expect that if at all it is built, the site is already decided that somewhere down the hill 30-meter telescope will be located somewhere here in comparison to other larger facilities at the site. In yellow circle is the planned site for the 30-meter telescope. And why it has been chosen? Because the clear and usable nights in Hawaii, Monarchia, is more than 75%, more than 3/4 of nights are usable. And water precipitation is also very less, altitude is very high, average temperature is minus 2.5 Celsius, and seeing statistics for 25% cases, the seeing is better than 0.4 arcsecond, and for 50% cases it is around 0.5. Otherwise, for all time it is sub-arcsecond that is being produced at this site. So why I'm highlighting about these parameters is that from astronomy point of view, for optical infrared astronomy, these parameters are really, really important to have a very good photometric or imaging or spectroscopic observations. So that's how this site is known as one of the best site in the northern hemisphere. And if you see that how large this telescope is, so I'm comparing with Delhi India Gate structure, and as you can see, this whole structure, once it comes up, the dome itself is around 55, 54 meter or something like that. So this physically this size of this telescope is really large, and that's how this telescope will look like, within the dome. And here is the truck, and in comparison to a truck also, you see how huge this full structure would be. And that's how this honeycomb structure is the primary mirror, and the feed would go to somewhere reflecting secondary mirror, and there is a tertiary mirror. And then on the Nesmith platforms, different kind of instrument suits will be kept all the way together to make best use of the telescope time. So this coming back to collaboration, that what exactly do we have? So this 30-meter telescope is a collaboration between Caltech, University of California, Canada, China, India, and Japan. And the idea is to build a 30-meter aperture telescope with a highly segmented 492 primary mirrors, 1.44 diameter each. That is, the diameter of each segment would be 1.44 meter, and such 492 segments would be put together to make it an effective radius of curvature of the order of 30 meter at the time of observation. And it's a 3-mirror approach where the flat tertiary mirror allows quick steering of the light into a suite of instruments mounted on the 2 Nesmith focus. And this is built-in post-focal adaptive optics system on one of the Nesmith platforms. Adaptive optics is a very advanced technology which have been used to apply corrections against the atmospheric turbulences, and this actually exploits the diffraction limited resolution, and it's beat the seeing, that is the atmosphere. So beating atmosphere is the whole game, that atmospheric turbulences are somehow accounted for, and this enhances the sensitivity to multifold, 50 to 60 times than the currently existing larger telescopes. And as you can see, that here is the primary mirror, secondary, and then tertiary. So the way here is a cartoon where you can see the light is falling on the primary mirror of 30-meter segments, and then reflecting back to secondary, and from secondary it is coming back to tertiary. And one of the Nesmith focus using folding mirror, either you can fed the instrument sitting on this platform, or for that matter if you flip it, then you can fed it to this platform, and so on, and many other things. So that's how this whole exercise is planned. And coming back to adaptive optics once again, I would like to pay your attention towards this UCLA, University of California simulation based on the real observations taken in infrared of the galactic center, that is center of our own Milky Way, taken at in K band, that is 2.2 micron. And in this image, this is overall a 6 arcsecond of sky, a very small patch of sky. And in this GIF animation, you can see that once the adaptive optics is off, you see quite a blurred picture, but if you switch it on, then you are really able to resolve those stars which otherwise are not seen. So that's the beauty of the adaptive optics techniques. So what happened in this technique is that here is the telescope aperture, where due to atmospheric turbulences the distorted wavefront is entering, and using a beam splitter, part of light is fed through a wavefront sensor, and part of light is again falling on something called a deformable lens or a mirror. And what it does, that the information which is coming through the wavefront sensor, it fed through computer, and using computers the measurement of this deformed wavefronts are fed to this deformable mirrors or lenses, and that's how it is corrected. And then after application of these corrections, the wavefront is supposed to be better, and that's how you can see the profile in here on the detector plane, which is a Gaussian having a very large FWHM, and after corrections you can see that how sharp it is. So this sharpness is produced using adaptive optics technique, and this technique is giving out a sharper image, and that's what you see in here. Using a telescope and a suitable instrument within 6 arc-second of sky of the galactic center, that is center of our own Milky Way, where we are expecting quite a chaotic place with a centrally supermassive black hole and so on. In K-band, you can see that once adaptive optics is off, you don't see things features very clearly. But once you switch on the adaptive optics feature, let us say Keck or any other existing telescopes like this of this class, then you are really able to resolve features and what kind of stuffs are there out in the galactic center. So this well-established technique is going to be scaled up for the 30-meter telescope, and the lessons learned with the 10-meter class telescope adaptive optics are going to be largely applicable to the 30-meter telescope. And that's how spin-off of this technology is there for societal benefits, where adaptive optics could be largely applicable to strategically important areas like space and defense, where using this kind of techniques, quite a good application and quite a strategic applications could be put in defense and space. And one small example, if you have got your eyes checked in any with any doctor having that computer controlled machine where a balloon is there, and if your eyes and chin are kept in a machine, then you are able to see that balloon structure. Actually, sort of adaptive optics kind of things are used there also to measure that what is power of your eyes and so on. So the point which I want to convey here, the take-home message is that the seeing limited absorption observations for the resolved sources, as I said in the beginning, it goes by a factor of d square, that is diameter is square. But if you apply adaptive optics corrections, then probably, I mean, we should be able to achieve sensitivity which could go as a d to power 4. So it makes a very large difference where such kind of a technology called adaptive optics it can produce a big difference in astronomical observations. All right. So what kind of partner work share is in the 30-meter telescope? If you see a segment cut where you are able to see half cut and how the telescope will actually look like and how big it is. So US as a partner of around up to 50% has decided that it will work on segments, polishing, civil works at the ground, integration and instruments part. Canada, one of the partners, have decided that it will work for the scallop type dome, adaptive optics system and instruments. Japan, with the companies like Mitsubishi and so on, it has decided that it will go for telescope structure, segment blanks, segment instruments and so on. China is ready to help building the tertiary mirror and the laser launching segments and instruments part. Whereas in India, we have decided that we would largely work towards crucial parts like M1 control system. The complete M1, most of the parts related to M1 segments, segment support assemblies and actuators and stuffs like that, it all comes under India's purview. A lot of software work we are doing towards the telescope project, segment instruments. In instruments also India is contributing. India has decided to contribute to a large extent. All right, so coming back to Indian role, what exactly we have planned and how we are going ahead. So in India, we have decided that in overall project of $1.5 billion now, I believe, uh, uh, we are at the level of 10%. So if we take numbers from 2014, then uh, India is partner at the level of 10%, and that 10% is translated in terms of money to somewhere around 1200 crores. And in terms of nights, 10% partner means out of, let's say, 365 nights, I mean 36 night would belong to India. So for money, it is around 10%, that is 1200 crores, and the cash contribution would be 30% of that 1200 crore. That's a common pool of common fund for infrastructure etc. And the 70% of our contribution would be in kind. So in kind contribution is important because in this we are going to provide a lot of subsystems, that is hardware and software, human resources, services, and so on. And institutional participation in India, now we have a structure, and this is led by India TMT Consortium, and three institutes since very beginning are involved, that is Aryabhatta Research Institute of Observational Sciences, that is ARIES, IIA Bangalore, and Inter-University Center for Astronomy and Astrophysics, IUCAA Pune. And it has been decided that India TMT Coordination Center, that is ITCC, would be there at IIA, being a lead institute, and things would be governed from here, and this project would be primarily funded by DST and Department of Energy under mega facilities for Basic Sciences program. And after these three institutes started these activities in 14 or even earlier, later on many other institutes like CDAC, Tata Institute of Fundamental Research, IIST, ISERS, and a lot of universities have also joined this project. And by putting hands together, we want to really proceed ahead and ensure that we contribute to this project to a desired level. All right. So as you can see the cartoon, the M1 segment, we are working largely towards M1 policy, and M1 means the primary mirror, and then the primary mirror control systems, that is actuator, edge sensors, a lot of electronics, segment support assemblies. We are also planning to work towards mirror coating, a lot of control software, and instrument development like WFOS, this is WFOS, FOS, and IRIS. So these kind of aspects are there where India is working already. And as you can see that if we take example of M1 mirror control system, then here is a kind of a layout of M1 control system where a single segment is actually sitting on a large structure called segment support assembly. This is a big, very precise optomechanical system having more than 80 components all the way together, and these components, all 492 segments, India is supposed to supply as a part of in-kind contribution towards the project. And as you can see that in Godrej and Boyce in 2014-15 itself, this prototyping has been demonstrated, and it has been established that in India we can really produce this kind of highly precise optomechanical systems. Similarly, on the below the segments where each segments are joining together, a lot of edge sensors for all 500 segments. We need around 3000 sensors. As you can see, they are put together so to ensure that all segments are kind of joined nicely. So these we are able to produce, and we have demonstrated that we can do that. And the actuators which are supplying in a controlled fashion, they are moving this, helping to move this control segment support assembly, these actuators have also been demonstrated that Indian companies can do it, and all 1500 such actuators we are expected to supply, and hopefully we will be able to do that. Apart from that, this 1.44 meter segment, so 90 such segments are going to be polished by India, and this technology has been transferred in Bangalore, Hoskote. We have a optics lab where this process has already been started, and we are supposed to supply 90 such polished segments. And here is a kind of as you can see, there is a primary mirror and then secondary somewhere and then tertiary. So a cartoon indicates that at both these Nezimuth foci we have big instruments sitting all the way on this Nezimuth focus, and just by using this folding mirror and moving it, it's possible to fed one instrument at a time. And these instruments, for example, planet formation image, or WFOS, wide field optical spectrograph. The size of these instruments are as large as a room of 20 feet by 30 feet or something like that, and these are really kept nicely to ensure that no time is lost um, to mount and unmount the instrument or to fed light. So that's how this has been. The whole design is made in such a way so that it should be fairly easy to fed one instrument at a time, and a lot of instruments as per specific requirements would be kept together. So that's how things have been decided. And if we compare that what we are in comparison to three large telescopes, that is GMT, TMT and EELT, then very different kind of instruments have been planned for different specific purposes. For example, if you need to do near infrared adaptive optics assisted imaging and integral field unit spectroscopy, then all three projects are going with suite of instruments for this purpose. If you have to do wide field optical multi-object spectroscopy, then also you have a comparable instruments with all these three projects. If you have to do near infrared multi-slit spectrometer, then also, for example, if you have to do high contrast exoplanet imaging, that is, if you want to image in the nearby stars that whether exoplanet is directly there or not, it's possible using adaptive optics technique. It is really possible to see orbiting planets around nearby stars, and for that TMT has a very specific instrument. If you want to do high resolution spectrometer, then also in TMT we have suite of instruments. So that's the idea. These kind of instruments have been decided for very specific purposes, and as you can see that the first light instrument, infrared imaging spectrograph or wide field optical spectroscopy we have in TMT. These are the two first light instruments which are really competing with corresponding GMT and EELT based instrumentation, and it is at par with that. Okay, so for example WFOS, as you can see that it's a 5 meter kind of size, and we have three optical benches where through slit mask and exchanger light will enter, and with this support struts it will go down somewhere here, and that's where a slewing bearing of the order of 5 meter diameter will be moving, and that's how the spectroscopy. So in comparison to a man of 6 feet height, you can see that how big these instruments are, the proposed for TMT projects. So WFOS, what it will do, it will take spectra of very faint objects in optical bands. The full advantage of a 30 meter aperture. The full wavelength coverage at low resolution is essential for characterizing very faint sources at very high redshift, maybe up to 5. Sky subtraction, the 10-hour integration time would be possible for to take faint spectroscopy, and it would be like important for to have this instrument so that using James Webb Space Telescope or LSST or gravitational wave follow-up are very faint sources, which is just not possible at the moment. We would be able to do that using WFOS. Another instrument which is important, is called infrared imaging spectrograph, that is ARIES, and as you can see, it will be deployable at one of the azimuth focus, and here is this imager section, and below down the integral field spectroscopic section will be there, and this full instrument will be kept at one of the azimuth focus because it is specially designed to exploit the spatial diffraction limit of the telescope at all wavelengths below 1 micron, larger than 1 micron, and it's the highest priority for the TMT because it takes full advantage of capability of 30-meter diameter and diffraction limit imaging, and it offers a range of capabilities that will be used for a broadband range of science programs. And this will be the first instrument where nefarious system will be used, that is narrow field infrared adaptive optics system, and that's what will make this instrument as a very unique facility. All right, in India to explore the science cases, as you can see, India, Japan, China, Canada, and US. US has a 41% share. India is around 20% share in international science development scheme, that what kind of science would be done. And if you see in India, what kind of interests do we have? So we want to work towards cosmology. We are interested doing early universe and intergalactic matter. We want to search and study supermassive black holes. We want to understand Milky Way and nearby galaxies, and stars also we have a lot of interest. Stars and planet formation, and then exoplanets, solar system objects also we have interest, and in time domain astronomy where a lot of transients are largely covered. So our interests is really considerably large among these kind of broad science goals. So that's how international science developments have been formed, and a lot of Indians are member in, and we are contributing that way. These international science development team have been formed, and their activities are given. That the detailed science cases 2015 have been already published. TMT legacy program across partnership science create real observing proposals with 30-meter class telescopes are discussed in here, and it's a continuous process, and it has been evolved in due course of time. People are working to update it. So that's where here is the link. If you are interested, you go through it and see that what kind of science would be done using TMT. It has been compiled with the help of ISDTs and TMT Scientific Advisory Committee working at that time. All right. So TMT Discovery Space, that is known unknowns. As you can see, here is a very simple plot. Those among audience not from astronomy can simply understand that here is x-axis is the time in days and y-axis is the brightness, and all known cases in time domain astronomy are plotted in a scattered way. As you can see that GRB afterglows are very bright, whereas some of the novae are very faint, but they are all known to a day and onwards. What is out there of the order of seconds to minutes and bright to faint limit is unknown. So we know that if objects are out there using 10-meter class telescope also, we know that there is nothing has been discovered in here. So unless we populate this area and try to understand this, we are not going to understand the transients and other time domain astronomy in a big way and in a large way. So the idea is to fill this gap, and that's where TMT kind of telescope is going to be contributing largely. That is known as time domain multi-messenger astronomy, and that is one of the areas where we expect that TMT kind of telescope will be really contributing significantly. All right. Here, if you see this plot, you see here is written Virgo. Virgo, it's a supercluster. When I am saying supercluster, it means it's a cluster of galaxies. So, as you know that our Milky Way is part of a small group, and that group is part of a galaxy cluster, and that galaxy cluster is part of Virgo supercluster. So if we believe that we are somewhere here, and if we believe that for this large diameter, this is somewhere 100 million light year, so you can imagine that how far I am talking about. I am talking about a big space where galaxy clusters are really associated like this, and you have very small gaps where there is nothing. Even using 10-meter class telescope, you don't see anything. That's defined as void, and these are defined as walls or filaments and so on. So in these superclusters, what we want to understand that if our Milky Way is here, then using TMT kind of telescope, it would be possible to study this large space and large volume, that what kind of large scale structure is, or in this nearby, I would say this as a nearby space, because once we say large scale structure, this is way beyond. But what I'm trying to indicate here, that at least up to in this volume space, all sorts of galaxies or known electromagnetic waves, or some hints about dark matter among these voids possibly which are there, we would be able to explore if something is there out. So these kind of goals are required to be achieved in near future. As we can see that we already know that only 0.4% matters are stars, and 3.6 are intergalactic gas, and this is all overall 4%, where we are able to see some sort of electromagnetic radiation, whereas 22% is dark matter, about which we do not know much so far, and 74% we believe is the dark energy, and about this part we really don't know. So as you can see, whatever we know, we know just about this 4% of universe. So 96% of universe is still unexplored. And in this direction, lot of efforts are going on, not only astronomy, but many other mega projects are also going on. I will come shortly what kind of activities are going on. But the point and take-home message is that we are eager to learn about unknowns. That is 22 plus 74%. As well as out of these 4% also, we don't know much. So eager to know about unknowns. That's the large goal. And if I talk a little more about spectral resolution versus spatial resolution. Spatial means, let us say in the imaging, if you talk, then how better in millisecond you are able to resolve. So this is the best spatial resolution which one would like to achieve, that is 10 millisecond to maybe 100 millisecond. This is quite a good spatial resolution and very demanding, which using cutting edge technology we believe that we will be able to achieve using telescopes like TMT. And then if you talk about the spectral resolution, then all the way from low resolution to very high resolution, and that's how different kind of, for example, if you want to do exoplanet imaging, then you need, surrounding a star, you need to understand if some planet is really moving around, and that's how this planet formation imaging instrument has been decided to a very high resolution spectral, high spatial resolution, and but very low resolution in spectral end would be required. Though if you want to do high resolution spectroscopy, high resolution optical spectroscopy of those exoplanets or ISM or IGM, then you need a very poor spatial resolution, but maybe spectral resolution is very demanding to understand high resolution spectroscopy and elemental abundance and what kind of ionization states are there. So you can see for the same planet formation imaging, depending on what kind of science goal do you have, you really need a very good balance between the required spatial resolution and required spectral resolution. So that's where this adaptive optics is playing role. And as you can see, depending on if you want to understand IGM structure, stellar population at very high redshift, then using WFOS, you need a very low resolution spectral, whereas very low spatial resolution. But if you want to understand exoplanets, gamma ray burst, intergalactic medium, then you need a spectral resolution very high and a spatial resolution also very high. So depending on that, we have to decide that what exactly do we want to do and what kind of science goals do we want to address and so on. And that's how things have been decided. So overall, in coordination with other upcoming mega and multi-wavelength, multi-messenger facilities, we would like to answer following broad questions. How and when the universe came into being? That's a big, large question. Last many decades, we are trying to understand, and further, with experience and earned using 10-meter class telescope, we should be able to answer. How did galaxies take birth and evolve, and what we see today? So, as you know, that a lot of galaxies are there. Millions of galaxies have been studied in great detail, but we don't understand that how do they take birth? Why did we get actually galaxies into elliptical and spirals and not other kind of galaxies? And whether spirals came first or elliptical came and how do they evolve is not known. What is the large scale structure of the universe? For example, I said that for up to 1 or 2 redshift, we know that how galaxies are evolved and so on, and how galaxies are distributed using Hubble ultra deep field and so on. But actually what's happening out there up to large redshift as large as 10, 20, we don't know. So unless we understand that what's happening out there at those large distances, that is redshift 20, it will not be possible to say something about large scale structure. Using computer simulations, we know up to certain extent that how universe might have been ionized and evolved, but we need to verify it. And that's where TMT would play a role. How massive black holes are. For example, we know supermassive black holes of the order of 10 to the power 4 to 10 to the power 9 solar mass, but do we have 10 to the power 3 solar mass black hole? Or in stellar black holes also, what is the minimum mass limit in black holes? That we do not know. Is there life anywhere in the universe? That's the exoplanet. Do we have life anywhere else in the universe? Do we have habitat zones somewhere in the nearby stellar sources? In nearby stars, do we have planets like Earth? And if at all it is there, what is the nature? Probably with the TMT, these kind of things we would be able to answer. Is there any other stuff we can see? For example, dark matter and dark energy? Probably in those directions also 30-meter telescope would be able to contribute significantly. All right. So along these directions, stuffs are going on, and among audience, to students, I would like to encourage that 30-meter telescope is one of the mega projects where India is putting a lot of efforts, and in ITCC, Bangalore, center is there where most of the activities are centered and other institutes are working together. And here is the website. If you want to understand, go there and understand more. In Nainital also, in ARIES, recently last year from 17 to 19 October, we hosted a big meeting where participants from maybe around 20 institutions and universities throughout the country joined hands together, and a lot of science and instruments and how should we proceed ahead were discussed at length, and around 150 participants throughout the country and locally participated, and a lot of students joined, and this was a good effort to advertise this project further and make sure that more people join hands. And here is another effort where among general public and among students, technocrats and scientists, universities, we tried to engage people, and it was a year-long effort where in Mumbai in May 2019 efforts were started. It was there for 2 months in Mumbai, and then it went to Bangalore. From there it went to November in Kolkata, and recently in from Jan to March 2020 it was in Pragati Maidan, New Delhi. And what we tried to showcase is that what kind of mega projects do we have in the country, using which in basic sciences we are trying to understand, and we are trying to build these mega facilities in the country. We are trying to engage Indian industries together, and this has been seen in a larger perspective where we also want to churn out possible societal benefits, that what exactly we are going to give back to the society by using this taxpayers' money. This was known as from micro to macro, understanding the universe through mega science projects. So if you little pay attention, this is a self-explanatory, very nice picture where if at all we believe that there was a big bang, and after that it was a point-like explosion, and at some point, as you can see, energy dominated universe got converted into matter dominated universe, and after matter dominated universe was created, probably we got forming first stars and then first galaxies, and then at some stage black holes and so on, and that's where the life on earth begins. So we presently we are somewhere here, and if we try to trace back, if you believe that we are here, and if you look back in time and you come here, let us say when Big Bang happened, then very less than a fraction of seconds, when probably neutrinos were first kind of entity to be born, probably that happened, and then at some stage a lot of high energy particle reactions and bosons kind of structures came in here, and maybe in few minutes we got some other structure where first nuclear reactions and things like that happen, and then of the order of a million years, 100 million years, we got first stars and first structures and first proto-galaxies and so on. And then in 500 million years or something like that, you have a structure of the very early universe came into existence. And then at some stage of the order of 1 billion years or something like that, thermonuclear reactions got established, and after that we had black hole formation, and of the order of few billion years or so, and then we have at 10 billion years or something like that, we have formation of stellar systems and so on. It is not well established, maybe earlier also this happened, we do not know, but based on observational evidences since last 50 years or so, whatever we understand is like this. So this is very rough diagram, and this is the present universe today. So now you come to those circles and those names written in here. So all the way, if we want to understand something very, very early, that what happened soon after Big Bang and so on. So to understand the nature of neutrino, probably those came very early, and that's where we believe that they came into existence. So if we need to understand those non-electromagnetic waves, then probably we need to have something like INO, that is Indian Neutrino Observatory. This is a very big mega project which has been planned that in South India somewhere below ground we will have detectors, and we will try to understand the nature of neutrino and how do they evolve and how many types of neutrinos are out there. Then India is also has a partnership to understand a project called CERN, and in CERN where Large Hadron Collider and experiments like that are going on, probably we have partnership, and probably we want to understand those things in detail. That's how we have a partnership in project called CERN. And then if we want to understand the nuclear reactions and how nuclear astrophysics evolved, and what kind of nuclear reactions are out there, and how exactly do they contribute towards evolution of the universe, then FAIR is a project. It's a antiproton facility where India is partner in, and SK is a square kilometer array. This is another big mega project where India is partner, and all the way from 100 billion years, when the formation of first star happened, first stars and first structure happened, then probably signals should be observable at radio n, because they are not absorbed on the earth, and that's how square kilometer array is the project where we want to understand at these distance and time scales about first stars and formation of first structures. And in the visible infrared, if you want to understand that what happened to the structure of early universe to a very far away distance, then that's where the 30-meter telescope is, about which I was talking about. And then using universe and using thermonuclear reaction and thermonuclear energy, if you want to understand, then that's how ITER project is there, International Thermonuclear Experiment. So this project is very, very important, because once we understand that how to use hydrogen as a fuel, then all problems of energy related issues will be solved to a good extent. And if we are able to tame hydrogen in a much better way and try to understand that how thermonuclear fusion reaction works, then fusion reactors would be possible. And since we have a lot of hydrogen at the moment, ITER partnership of India in ITER has been very, very great success, and the Q factor is still I would say less than 1, or in for fraction of seconds we have got to a Q factor of few. When I say Q factor, it means if you are giving X amount of energy, then the kind of energy you are getting output is the Q factor. And this Q factor indicates we are trying to enhance it to maybe hundreds or something like that. Maybe in next 20 or 10 to 20 years it will be possible. And once Q factor is increased, then you can see the societal benefits which we can have from the ITER project. And then LIGO, the Laser Interferometry Gravitational Wave Experiment. Recently, India has planned that it will join hands to put its own gravitational wave detector in India. And that's how we want to understand the chirps from black hole, the black hole structures, the black hole mass estimation, what kind of gravity waves are, and these are the non-electromagnetic part of the spectrum. And now we know much about electromagnetic. Maybe if we understand and detect non-electromagnetic part of the spectrum, that is gravitational wave, then it may have way out applications which have been not yet thought about. So the whole idea is to detect more and more gravity waves and try to understand their nature and how do they evolve. And here is the present universe. So these kind of projects are there, and these kind of mega projects have been really been planned in India, and you can see that they are of crucial importance to understand the universe. Not only universe, how universe evolved, do we have planets out there, do we have habitat zone, all the way from that to converting hydrogen into energy and enhancing Q factors and so on. So with these projects, a lot of societal benefits are there. Young students and technocrats are really, really highly encouraged to work towards these projects, because ultimately the future of Indian science is largely going to be based on the success of these projects. And if we really contribute significantly, then probably in India we are going to be the leaders. Thank you very much. So yeah, so we have very few questions. One of the learned person, Pradeep Chakravarti, has questioned that there are some glitches regarding the selection of TMT site. Have those been sorted out? Yes, that has been sorted out, and hopefully the construction will be on soon. And the second question from him, what is the venue where the assignments allotted to India will be carried out? I don't understand this question very clearly. What is the venue where the assignments allotted to India will be carried out? Okay, the second part is clearer to me. that what kind of assignments India has been given. So if you have seen my talk, and if you have heard my talk carefully, you might have seen that lot of ongoing hardware related packages are there. And if we talk about segment support assemblies, actuator and edge sensors, then a lot of progress has happened, and we are in a position to contribute and to produce them. For example, the segment support assemblies are currently in the process of getting finalized to be manufactured in one of the units of L&T. Thank you very much. Those who have not been able to listen me about this 30-meter telescope project under this talk right now may follow our Facebook and YouTube links through ARIES web page or even otherwise, and can listen it again. And if you have further questions, then do write emails to me. Thank you very much.